Next, we're going to look at an example of a t-test, which works extremely similar to the z-test. So let's kind of go over the general idea at first here. So you've got a null hypothesis and an alternative hypothesis. For the t-test, you're talking about a single mean, so the null hypothesis has to be that mu is equal to some value that we'll call mu sub 0 to match the null hypothesis. And then you would compute your test statistic. I should have a sub 0 here. It's x bar minus mu, and we take mu from the hypothesis. It'd be this number mu sub 0. And then we would divide by s over square root of n, the sample standard deviation over square root of n. That would give you your test statistic. And then you would compute the probability from the t-distribution with n minus 1 degrees of freedom based on the sign of the alternative hypothesis, which could be one of three things. I got some pictures that are going to pop up here. If we have mu is greater than mu sub 0, we'd have a picture kind of like this where we're doing the area to the right, greater than on the picture, a one-tail test. If mu is less than mu sub 0, we have a picture where we're doing the area to the left, still a one-tailed test. And then if we have mu is not equal to mu sub 0, depending on whether our test statistic is positive or negative, we're looking for the area either above or below the positive and the negative value. It's a two-tailed test. And your p-value would be those areas. And it says these p-values are exact if the population distribution is normal, and they're approximate as long as we have large n sizes in other cases. So let's do an example. So this one says a college student thinks that the average student at her college studies at least 5 hours per week. A random sample of 15 students was selected from the student body, and the table below shows the number of hours that each claims to study per week. So we have this table here with 15 responses here where the students said how many hours they study per week. And of course, how accurate is that data coming from the students themselves? They may be over or underestimating, but we're going to take that as our random sample there. Check the assumptions for a t-test. So we do have a random sample. The college population would be much larger than these 15 students, so we're okay with that. The sample size is 15, so we do have to worry a little about normality, and I'll talk about that in a second. And we're going to carry out the t-test, and our hypothesis is the null always has to be an equality. The student thinks mu is going to be greater than 5, so that's going to be the alternative hypothesis. But the null hypothesis has to be that mu equals 5. We have to have equality to set up the distribution. So I have some pictures here. The first thing I'm going to do is look at what's called a residual plot, which will help us check that assumption that the sample distribution or sample data is approximately normal. Let me bring up my actual calculator. I have the screenshots, but I'll show you live on the calculator. Okay, so the first thing I'm going to have to do is enter the data. So I'm going to do stat, edit, and I'm going to clear out this list 1 and type these numbers in. I'm going to go ahead and pause. Well, let me type a few of them in. 4, 2, 2, and so forth. I'm going to type in all of these numbers. I'm going to pause the video so you don't have to watch me do that. Okay, so I took the time and typed in the 15 numbers here. So in L1 I have the list of these numbers that are all the student responses to how many hours per week they study on average here. So if I want to test the assumption, since I have them in there anyway, if I want to test the assumption of normality, one way to do that is with what's called a residual plot. And what this does is it plots the z-scores versus the actual values themselves. And if that is approximately linear, and we can tell by looking at the picture, then that means the data is close enough to normal to be able to carry off the test that we need in terms of that assumption. So I can do, first let me do y equals, make sure I don't have any other graphs in there, and then do second y equals. We set up our plot, and it's the very last option that you get. Okay. If you go all the way to the end of the list, that one's the residual plot. And so your options, it asks for a single list. This is a one variable graph. Okay. It's going to plot on one axis, it's going to plot the actual variable that I have in L1, and on the other axis, and I can pick whether I want to do the x or y axis, it will plot the z-scores for all of those is what it will do, and it doesn't really matter here. I'm going to leave that as the x-axis and pick what you want it to do for the points. I always use the little squares. And I'm going to do zoom 9, which makes sure the data fit. And you can see that looks like a pretty strong linear approximation. Okay? So we're going to be safe to use the t-distributions in this case. And then it's pretty simple from this point. We've already put the data in. If you're allowed to use the calculator to do this, we can do stat, go over to test. And on a previous problem, I was doing confidence intervals. That's down there at number 8, but t-intervals up here at number 2. And this time I actually have the data, so I would select data. And then we put the null hypothesis value. This time we're assuming mu equals 5 in the null hypothesis, so we'll set that to 5. And then my list is where I put the data. That's an L1. I'm not using frequency lists, so I'm going to leave that at a 1. And let's see, our alternative is greater than, so make sure that was selected. And then either calculate or draw, depending on whether you want to see the picture. I'm just going to do calculate. And so we get a test statistic of 2.24 if we rounded it, and a p-value of about 0.02. Okay? And then it gives you some of the summary statistics there. But we have a small p-value. Let's say we're going at alpha equals 0.05. We would reject the null hypothesis. Okay? If the actual number was equal to 5, we would expect to get this type of data less than, about 2% of the time. So it was very unlikely we would find these numbers if the real mean was equal to 5, so we would conclude, yeah, it looks like the student's right. We have pretty good evidence here. It's what we would call significant evidence that the students at this university, whichever one is in the problem here, the college in the problem, study more than 5 hours per week, that it's not 5 hours per week. So we would conclude in the direction of the alternative hypothesis. I have the screenshots for that, so you see the picture there. I'm selecting the residual plot. There's a picture of the residual plot, which again looks pretty close to linear. So we have a random sample from a much larger population, and the residual plot shows a fairly strong linear form. Thus, the sample is not too far from normal. We're okay to do the T procedures. So again, you hit Stat, and then go over to the test menu and choose number 2. And you set up your information and hit Enter, and you'll get there your results. That T was about 2.24 if we rounded, and P is about 0.02. So we have a sample mean of 6.8 hours, which is larger than 5, and it turns out the test statistic is 2.23. Now, technically, what's that saying is measuring by standard deviations of S over square root of N, that the sample mean of 6.8 is that many, 2.23 standard deviations above 5, the hypothetical mean from the null hypothesis. And the probability that that would happen, that we would get something that big, if it was really 5, is only about 2%. Which is less than 5%. If that's going to be our cutoff level, we have significant evidence, as I say here, that students at the university do study more than 5 hours per week on average.